In an earlier video, we saw how the matrix 3, 1, 1, 2 mapped the Cartesian grid of squares onto a parallelogram grid. If we start off just with this little square here, OACB, that was mapped onto OA dashed, C dashed, B dashed. The little square just next to it was mapped onto the next parallelogram along, and so on, so that the grid of squares that we start with becomes a grid of parallelograms. Let's just look and see where the point 2 minus 1 goes. That becomes 6 minus 1, that's 5. 1 times 2, 2 times minus 1, that's 0. So we know that that goes to the point 5, 0. So that is, starting with the point 2 along, 1 down, it finishes at 5, 0. But I don't have to calculate it once I've got the grid. I can just go 2 parallelograms along, 1 parallelogram down, and I get to 5, 0. So that the parallelogram grid really does describe just how this transformation works. We all know that the area of this little square is 1. I know that the area of this parallelogram is 5. And I'll let you into the secret of that later in this video. So each small square becomes a parallelogram of area 5. Let's just look at a shape of 3 small squares made up like this, up, across, down. So I have 3 small squares. Those 3 small squares will be transformed onto 3 parallelograms, like that. So in this case, we start with an area of 3, and is mapped onto the 3 parallelograms an area of 15. So the area factor is 5. And that just happens to be the same as the determinant of m. If you work out the determinant of m, you get 3 times 2 minus 1 is 5. Now that will work whatever shape I start with. I started with 3 squares, I got 3 parallelograms. The area was 15 times as big. If I started with 9 squares, I would get 9 parallelograms, an area of 5 times 9, 5 times as big. So this, we will now go ahead and prove that the area factor is actually the determinant. In general, let's take the matrix M as A, B, C, D. Then A, which is 1, 0, will be mapped onto the first column, which is AC. So A is mapped onto AC. This length is A, this length is C. And B, 0, 1 is mapped onto BD. And so the distance across is B and up is D. Well, now let's look at a rectangle surrounding our parallelogram. The first length is A. This length is B. It's the same as the length here. And this length is D. It's the same as the length there. And so on. A plus B is the length right across. So we can calculate the area of the parallelogram by taking the area of the rectangle and subtracting that rectangle, BC, and that one, this triangle, half AC, and that one, same thing, and this triangle, half BD, same thing. This gives us that the area of the parallelogram must be the area of the rectangle, which is A plus B times C plus D, minus the two rectangles BC, that's minus 2BC, minus the two triangles half AC, 2 times a half AC is just AC, minus the two triangles a half BD, 2 times a half BD is just BD. Working that out, we get AC plus AD plus BC plus BD minus 2BC minus AC minus BD. And if you look there, AC disappears with AC, BD disappears with BD, AD, and then I have BC minus 2BC, that's minus BC. And that is just the determinant of M, which is the result that we wanted to find. That the area scale factor of a transformation with matrix M is the determinant of the matrix M. Let's see how we can use this. If we have a transformation S, which is represented by the matrix M, 3, minus 1, 1, 2, then the triangle T, A, 1, 1, B, 2, 4, C, 3, 0, is mapped onto T dashed by M. Show T and T dashed on a diagram and use the determinant of M to find the area of T. I've done that for you, and I've drawn the diagram for you so that you can see what is going on. The question now asks us to find the area of the triangle T, which is the blue one here, and the purple one is T dashed. Well, to find the area of the triangle T, if you look at that, there are no nice things about that. It would be an awkward question to do. But if we look at the triangle T dashed, we see that it is a nice, happy, right-angled triangle, and we know that the length of that one is 7. It goes from 2, 3 up to 9, 3, and this goes from 2, 3 up to 2, 10. So both of those lengths are 7. So the area of T dashed is a half times 7 times 7, which is 49. Oh ho, what happened there? Which is 49 divided by 2. The determinant of the matrix is 3 times 2 minus 1 times 1, which is 7. And so 7 times the area of T is equal to the area of T dashed, and therefore the area of T is 1 over 7 times 49 over 2, which is 7 over 2. You can find more about the area and the determinant in your textbook FP1 on pages 101 to 103.